Okay, these are going to get a little trickier because we've got some more forces involved. So we've got a rightward force is applied to a book in order to move it across the desk with a rightward acceleration. This time we are considering frictional forces, but we're neglecting air resistance to keep it simple. So a keyword here, rightward acceleration. I know right there that those arrows are not going to be equal because it's not balanced, it's accelerating. So if it's accelerating, it has to be unbalanced right there. So we know that we're going to have gravity going downward. Before I pop up the answer, I want to kind of talk you through it. Gravity is going to be going downward, and the upward direction will have the normal force because it's resting upon the table. We know that there's a rightward acceleration, which means it has to have a rightward applied force. In the opposite direction of that, we have to have friction, but we know that those arrows will not be equal. So the applied force here and the frictional force here, it's accelerating in the rightward direction. That's why this arrow is longer than friction, and friction will always be in the opposite of the applied force. Next, we have a rightward force is applied to a book in order to move it across a desk at a constant velocity. We're considering frictional forces this time, but we're neglecting air resistance. So keywords here would be constant velocity. If it's a constant velocity, I know that it has to be balanced. So those arrows, because it's balanced, are going to be equal. It should be pretty similar to the last one. We know we're going to have the force of gravity going down. It's resting upon a table, so the normal force has to be opposing that in the opposite direction. Those two should be equal. Again, we're going to have a rightward applied force, and the opposite, we're going to have a frictional force, but that's simply going to be equal in length, which is what's keeping that object traveling at a constant velocity because these two forces here are balanced. Okay, a college student rests a backpack upon his shoulder. The pack is suspended motionless by just one strap from one shoulder. Keywords here, we're going to have motionless, so therefore it has to be balanced. We know that picture a book bag hanging, gravity is going to be what's pulling the book bag down. Because it's balanced, that tension force, anything hanging is going to be a tension force, is going to be going in the opposite direction. Okay, next we've got a skydiver is descending with a constant velocity. Descending just means falling. Keywords here, constant velocity, and that would be a balanced force. We know, again, picture someone skydiving. What's happening there? Gravity is going to be pulling them down. What's the opposite force if you're falling? If you're falling, it has to be air resistance. This would be an example of terminal velocity right here, where gravity is balancing air resistance, which is causing it to travel at a constant speed. Okay, next we have a force is applied to the right to drag a sled across loosely packed snow with a rightward acceleration, that would be the keyword, rightward acceleration. We know that those arrows will not be equal. It is going to be unbalanced. Think through our forces here. We're going to have gravity going downward, normal force going upward. The sled is going to the right. That's the applied force dragging the sled, which is why that's longer than the friction. There's still some friction in snow, just less than what the applied force is here. Okay, a car is coasting to the right and slowing down. A free body diagram looks like this. Keywords here is that it is slowing down. So again, if it's slowing down, that is just negative acceleration, which would be an unbalanced force. This would be gravity still going downward on the car. Normal force would be going upward because it's resting upon a surface. It does not say anything about an applied force if it's slowing down. That's why we just have friction to the left here. This is an example of a tricky one. A lot of people want to put a force right here just because it's coasting to the right, but there's no force being applied there, which is why it's slowing down in this direction. And that's it.